Well, the goal of this exercise is to produce tree species maps from hyperspectral imagery and some ground reference samples. There are several potential methods to do that. Today, we'll be using machine learning algorithms. To get started, open the Applications from the main menu. Select Classification and then Classification Workflow. A pop-up window opens and, as you can see, some assistance is provided at the right-hand side of the panel. Now, let's first create a training dataset. Within the Regression Workflow pop-up window, click on the blue application wheel icon next to Training Dataset and choose the first option. Create Classification Dataset from Categorized Vector Layer and Feature Raster. Then, select the following settings. Choose the shapefile with the point data of all sampling locations as input for the categorized vector layer. Select the HyMap image as input for raster layer with features. If you have the two datasets open in a map view, they will be selected automatically. Next, open the Advanced Parameters drop-down menu and select Tree Spec in the Field with Class Values field. In the output dataset, I just keep the temporary file option. By clicking on Run, the process starts. For each sampling point in the shape file, the full spectrum of the corresponding image pixel is now extracted. Once the training dataset generation is complete, we automatically get back to the main regression workflow window. The temporary pickle file we generated in the previous step should automatically be placed as training dataset. For the classifier, choose SVC RBF kernel, which is a support vector machine classifier. Now, machine learning algorithms such as support vector machines typically require a parameter tuning. That is, we try to identify the optimal settings of the classification algorithm by splitting the dataset into several parts, and then use some of these parts to train the classifier with a set of parameters, and then validate them with another part which has not been used during training. By repeatedly varying the parameters, we can find a combination of parameters that performs exceptionally well. In the case of SVM, we can vary two parameters, gamma and cost. Gamma defines how flexible the so-called hyperplane is allowed to be. The hyperplane is basically the separation line between the different classes in the feature space. On the other hand, cost describes how strongly the classifier punishes a wrongly classified sample. If cost and/or gamma is too high, there is a risk of overfitting. For now, we stick with the default settings. However, feel free to try out some higher and lower values if you are interested in the results. Below the Code Snippet box, select the original HyMap image in the Raster Layer with Features field. The number of cross-validation folds is set to 10 by default. This means that our 250 training data points are split into 10 groups with 25 samples each. Of these groups, 9 are used for training and 1 for validation. That means your results will likely differ a little as the algorithm will use a different set of samples in each run. You can leave all other options on default too. I just quickly set the memory options now. And click Run. Okay. Running the classification workflow takes a few seconds. Once finished, an HTML file opens in your browser, showing the results of the selected classifier. Now let's look at the SVC performance report. From the confusion matrix, we can deduct that Fagus sylvatica, beech, was confused a fair bit with one of the oak species, and vice versa. Also, the coniferous species could not be differentiated from each other ideally. Meanwhile, the red oak was predicted fairly accurately. The mean overall accuracy of approximately 78% is quite good. In the EnMAP-Box, there is now a SVC classification layer that contains the tree species map we just produced. You can display the file by right-clicking on the layer, choosing Open in New Map, and selecting Default Colors. For better comparison, I link the tree species map with the color infrared display of the HyMap image. And I assign the colors we use to represent our vector data to the map as well via the Layer Properties menu. At first glance, this map looks quite plausible. We can see that many of the training data were collected, and we hence know that they are composed of a single species, appear quite homogeneous in the classification map. If available, you can use further reference data to compare and validate your classification. In our case, we have a detailed reference map that we can add to the EnMAP-Box and display in the existing window of our tree species classification. Via the Layer Properties menu, we can set the transparency to 30%. The result allows us to check our classification result against the map of forest stands. Well then, one way to improve the accuracy of supervised classifications, particularly when working with hyperspectral data, are feature extraction methods, as they allow to compress the feature space and hence reduce collinearity of predictors. In the following, we will apply the well-known principal component analysis, PCA, to the hyperspectral image to reduce the original 125 bands to a smaller number of bands carrying most of the variability contained in the image. For this, we will need a tool which is not located directly in the EnMAP-Box, but in the processing toolbox of QGIS. Go to the Processing toolbox and search for PCA. You will find Fit PCA, which is part of the EnMAP plugin. In the code snippet box, you can see that the number of components, N components, is set to 0.95. This means that the number of components that explain 95% of the variance are to be calculated. If you want a higher percentage or a specific number of components, you can change the setting. Enter an integer number, for example 10, if you want 10 components to be calculated. Leave the field Raster Layer with Features empty. In the example below, we use 1000 sample points. The more points are used, the longer the PCA calculation may last. In Advanced Parameters, click on the gear icon and select the first option. Create Unsupervised Dataset from Feature Raster. Here, select the HyMap image as the Raster Layer with Features and the tree species as Mask Layer. Make sure to save the result in the Data Results folder when returning to the previous window for the transformation, and run the model. Next, we apply the PCA to the raster layer. For this step, we use the tool Transform Raster Layer from the Processing toolbox. Select the HyMap image as the raster layer and the previously created PCA model as the transformer. Save your result and run the tool. OK, I add the result to the map window. It's a simplified version of the data with only 3 bands that represent the PCA components. In our case, 3 components explain 95% of the variance in our dataset. Now, let's run the same SVC classification as before, but using the PCA transformed input data. Select the layer PCA transformed in the training dataset as well as in the raster layer selection as input. Run the tool. Again, the performance report opens automatically. Often, we achieve better results with a reduced number of bands instead of all bands. However, obviously not in this case. Still, if you compare the map to the preceding classification, let me just quickly copy the style to make them more comparable, they look quite similar. Finally, let's look at another classifier. For comparison, I use the popular random forest classifier. Random forest is another machine learning method that copes well with the large number of spectral bands that we have in imaging spectroscopy. Here, the outputs of multiple regression trees are averaged. I go to Applications and select Classification Workflow. To generate my training data, I click on the gear icon and select the first option. As before, I select the tree species as Categorized Vector Layer, the HyMap image as Raster Layer with Features, my tree spec as Field with Class Values, and click Run. Back in the Classification Workflow main window, select Random Forest Classifier as Classifier and the HyMap image as raster layer with features. If you like, you can save the map as classification layer and the performance report. In this case, I also save the output class probability layer. Yet again, while random forest is popular for a reason, it seems that the support vector classifier is the more suitable classifier in our specific case. With about 0.69, the overall accuracy is considerably lower than our first results. In addition to the tree species map, we got a probability layer too this time. Give me a second to load them both to new map windows and assign the style. Now, if we compare the classification results in a map view, they are not spectacularly different. The SVC seems slightly better at differentiating the oak species, while the combination with PCA improves the classification of pines. All algorithms have difficulties with beeches that do not occur in pure stands. To exploit the probability layer, we can use the tools from the main menu. Choose Raster Statistics, and then Class Fraction / Probability Renderer and Statistics. In the window that pops up, I choose the probability layer as input and copy the coloring style. By checking and unchecking boxes, I can now display the probability that a given pixel was assigned to a certain tree species class, while in the classification map, I do only see the highest probability and thus the class to which a pixel was finally assigned. Well, that's it for today, folks. I leave you to interactively explore your maps. By the way, there are even more tools to explore classification statistics in the EnMAP-Box. I'll link a description below. I hope you enjoyed our little exercise, and I'll keep my fingers crossed for your future analyses.